Okay, so now we are going to take a look at another aspect of chemical reactions that we haven't really addressed so far, not just in General Chemistry 1, but also in General Chemistry 2. And just give you a quick recap of where we've been so far. So we've seen when we talk about the rates of reaction or rates of reactions, right, which is chemical kinetics. Really, what this is telling us is how quickly reactions happen. And what we're going to be taking a look at in this section is going to be something slightly different as opposed to exploring how quickly reactions occur. What we're going to be doing now is we're going to be taking a look at the extent of a chemical reaction, or the extent to which a reaction occurs. And this is going to be encompassed in this topic that we're in right now, which is going to be chemical kinetics. I'm sorry, chemical equilibrium. We have sort of just briefly glossed over equilibrium back in General Chemistry 1 at some point. Now we're going to take a much closer look at what's occurring here. And also to give you a recap of where we've been, especially in General Chemistry 1, the assumption was when we have a chemical reaction, okay, so we're going to start off with one or more reactants. And reactants are always on the left side. They react together to produce the products on the right. And we always assumed that this reaction will always produce products. Which means that we're also assuming that no reactants are left behind, or no reactants left over. What we're going to see is that we're going to not necessarily turn this on its head. We're going to add another layer to this idea. Now, we'll take a look at a very simple sort of introduction to this. And the very first sentence here is very important. It says, most chemical reactions do not start with only reactants and go to only products. So that is just different to what we've been exposed to so far. And the other part of this first paragraph here is that they do not go to completion. In other words, if you start off with a particular reactant to begin with, the assumption that we had before was that all of that reactants would be converted into products at the end, so that reaction would go to completion, right? So that's what we're assuming, but that's what we have been assuming so far. So this reaction will go to completion and we'll have nothing left but products at the end. What we're saying is that is not actually the case in the vast majority of cases. Instead, what we're going to see is that most reactions will start when there's a mixture of reactants and products, or products and reactants. And we'll take a look at a very simple example to illustrate this. Right? An example here is dinitrogen tetroxide reacting to produce nitrogen dioxide. So let's say we're going to start off with a certain amount of the reactant. So we have our N2O4. And let's just say this is our reactant concentration to begin with. We're going to start off with a certain amount of this, and this is just the progress of the reaction on the x-axis. So obviously at the beginning, at time equals 0, we have only reactants present. And what we would expect to find is that as time passes by, the amount of reactants is going to decrease. And we would assume that that will decrease all the way down to 0. However, what we actually find is that the reactants concentration do decrease as their concentrations or as they're used up, but then eventually that rate of decrease slows down until we end up with a constant concentration of reactant. Simultaneously, what we observe is that not only can we plot the reactant concentration of on the x-axis, we can also plot the concentration of the products on the y-axis. So originally for the products, right, we have no products to begin with, so we're down here at 0. So obviously now we would expect that as the reaction proceeds, the amount of product that we generate is going to start to increase, and we would expect that to be a linear increase like so. What we actually find is that, yes, the reaction or the concentration of the products increases, but then it starts to tail off a little bit. And then what we find is that the concentration of the products actually start to stabilize, or they become a constant value, right? And this is different. This is, in some cases, very different than what we looked at previously. This is really what is occurring in most, if not all, chemical processes. And what this illustrates is not only are the reactants being converted into products like we would expect, but at some point, the products, after they're generated, they actually start to be converted back into the reactants. So what we have, right, are these two processes occurring. So obviously we have a forward, let's say left to right. We refer to that as our normal traditional reactants or reaction that we've looked at previously. This is called a forward direction. Okay, and then we have the right to left occurring. You can probably guess where I'm going with this. This is the reverse reaction happening simultaneously when enough of the products build up. So we refer to this process as a reversible process, because not only can we go from left to right, we can also go from right to left. So we often see this being represented with a double-headed arrow in both directions. Or sometimes you'll see a half-headed arrow in both directions as well. Okay, so a half-headed arrow this way, half-headed arrow that way. We have products. Reactions are still on the left, products are on the right, like it is normally. But this is the extra layer now that we're going to be introducing in this particular section. So that's a general example. The example up here, the N2O4 breaking down into NO2. This is a very similar example. This is a reversible process, and that's the term that we'll use. Not only can we go left to right, reactants to produce products, we're also going from right to left, products reacting to form reactants in the first place. Now, what we are going to see, as we've established in this diagram here, is at some point, what we're noticing is that maybe at this time point, right about here, the concentration of this was the reactants, right? The purple one was the reactants, was constant, right? It was a flat line. And then we also saw at that same time point up here in the green, which is the concentration of the products, that's a flat line as well. So here the concentration of the product or the products was constant also. What we say is when those concentrations of the reactants stay the same, constant, when the concentration of the products stay the same, we say we have achieved a state of equilibrium. All right, so we say the system is in equilibrium. And what happens here is at equilibrium, and we're going to abbreviate equilibrium as EQM from this point onwards. So at equilibrium, the concentration of the products, okay, is a constant, doesn't change. We're also going to see that the concentration of the reactants is also a constant, doesn't change. And the reason why these don't change is because we can now tie in something we learned from the previous chapter, the previous section, because the rate in the forward direction, left to right, is equal to the rate of the reaction in the reverse direction. Okay, and that is that's the condition that leads to, that's the criteria that needs to be satisfied for us to achieve this equilibrium process, right? So it's not that, and it's a very common misconception, it's not that the reaction has stopped, okay? So we'll just put this as a note down here. The reaction has not stopped. Instead, right, what we find is the rate. So the rate at which the same rate as which the products are converted back to reactants. And as a result, we see that the concentrations of each of those do not change. We can monitor that using a color, for instance, if your reactants and or products have a color associated with them. Right, so for example, in the specific one we looked at above, if you start with your N2O4 up here, right, the N2O4 has it doesn't have a color associated with it, but NO2 does. So as this reaction proceeds, we're going to be generating, so the N2O4 is colorless, whereas the NO2 is brown. So as this reaction proceeds, we generate more NO2, the brown color will start to increase, right? So this is what we're noticing down here. And at some point, maybe around this time, the brown color stays the same. So that means then that the concentration of the brown stuff, the NO2, right, is constant. So at this point, and then similarly at that same point, the concentration of the N2O4 is also constant, right? They may or may not be the same value. That is really not the point of this. The point of this is that their concentrations are not changing once we've established equilibrium. Okay, so sometimes equilibrium is referred to as dynamic equilibrium. Okay, so it's not a static equilibrium. We refer to it as dynamic equilibrium or just simply equilibrium, right? We just get rid of the dynamic as the first word. And that is to reinforce the point that things are still happening, right? You still have reactants turning into products, but the rate at which that's occurring is the same rate at which the products are turning back into the reactants. Now, the example that's shown up here, we can start with either, and because it's a reversible reversible process, we can start with just reactants. And we'll see that the concentration of NO2 increases, concentration of N2O4 decreases. We could also start with only products. So for instance, we could start off this procedure here by having just a bunch of NO2, and we'll see the same thing occurring. So if we start with NO2, as shown over here, right? Now the NO2 is the thing that has the brown color associated with it. So what happens then is the color fades, because all we have to begin with is the NO2, until eventually at this point here, right, then the concentrations, we've established equilibrium. Here now, from this point onwards, the color is unchanging, right? And that tells us then that we've achieved equilibrium at that point. The rate in the forward is equal to the rate in the reverse direction. So again, equilibrium means that we've achieved the state where the concentration of the product is the same, concentration of the reactant is the same, they're not changing, and that's because the rate of the forward reaction is equal to the rate of the reverse reaction. Sometimes it's difficult to sort of interpret or rationalize or visualize what equilibrium is. We'll give you a simple analogy for this process. So imagine you go to the gym, all right? And let's say you hop on this thing. So hopefully my artistic ability here is good enough that you can understand what this is. This is a treadmill. Okay, and obviously the way that the treadmill works, right? You turn it on, and then the tread on the treadmill moves in this direction. Okay, and then you have a person standing on the treadmill. Okay, they're happy to be there. And in order for the treadmill to do what it's supposed to do, in order for you to reap the benefits of the treadmill itself, guess what? When you turn on the treadmill, let's say it's moving in, you set it as at a speed of, let's say, 5 miles per hour this way, okay? You then have to move with the same speed in the opposite direction, right? 5 miles per hour going the other way. So what we have here is the rate or the speed of the treadmill going left to right in this particular diagram is equal to the rate or speed of the person going in the other direction, right to left. And then when you look, if you're an observer in the gym and you're looking at this person on the treadmill, what you actually see is that the person isn't going anywhere, right? They are still moving, right? Stuff is still happening. The tread on the treadmill is moving. The person is pumping their arms, moving their legs. They're sweating profusely. So stuff is still happening. However, the person isn't going anywhere. So it's a state of equilibrium, right? The person, it doesn't look like anything is happening in terms of the position of the person, but there is still a bunch of stuff going on. So it's dynamic also, right? But the key thing here is the rate and the treadmill, the speed in one direction equals the speed of the person in the other direction. That's an analogy. Sometimes it resonates with people, sometimes it doesn't. But I think it's a good way to kind of think about what that dynamic equilibrium is, and can just, shrink this down to a microscopic and submicroscopic level. That's what's happening in your chemical reactions.